Hi, everyone. I mean, I don't need this chart to tell you how bad it's become, right? It's literally a hot topic the last year or so. I think when we looked at this chart last year, 9 out of the 10 hottest years was last year. Last year broke a record, so this year it's 10 of the hottest years are the last 10 years, as you can see since 2014. Numbers are rising rapidly. I think you feel it, definitely you feel it in Singapore. And when I was in Shanghai towards around 2014 to 2016, towards the end of it, 2016, you're seeing the record temperature elevating in Shanghai itself. Shanghai, a lot of the older housing, they tend not to have heating or cooling. The older folks love opening the windows, adapt to heat and adapt to cold accordingly, and also depending on what they wear. But the temperature got so hot then that they started resting in MRT stations because it's air conditioned. So you see people bringing family and lying around in the stations just to escape from the heat. And I was in Sydney when the record bushfire season happened as well. Yeah? You know, you had the Black Saturday and then the Black Summer. That was in 2019 to 2020, where about 250,000 square kilometers of bushland were burnt. So this affects, definitely affects how we live our lives. And even from modeling and from reconstructed temperatures and then the observed temperatures, you can see how drastic the numbers have become. Oops. And in Singapore, the numbers obviously since 2000 has been elevated, so it's close to the average 1 degree temperature rise globally. And obviously this affects not only our comfort level, but even in terms of workers, migrant workers working out in the open. And from the numbers, I think in Singapore, you're looking at averaging about 34 deaths from heat in work-related incidents per year. And we are also looking at increasing number of people being hospitalized due to heat. I think earlier speakers talked about vulnerable population, etc. Definitely they're more vulnerable. And it's not helping Singapore's population numbers because fertility gets affected as well from elevated temperature. Also, in terms of economic impact, right? You get less people calling in sick or just not able to work because of the elevated heat, and it translates down to the economic costs for the country as well. So in terms of urban heat island, I won't have to explain much on this. Within urban areas, it's a lot warmer compared to the rural areas. And the contributing factors in terms of building geometry, in terms of how we do the building fabric, anthropogenic heat. We had the talk on data centers. Yes, it contributes towards anthropogenic heat in terms of heat being thrown into the environment, and also surface cover, whether it's tree covered, whether it's grass, etc. And globally, I think the impact on environmental, this economic costs, which I spoke a bit about earlier, and also in terms of health and inequality. I think the vulnerable population, whether they are older, the young, when we map out where they live in the city and then where it's hottest, it affects them tremendously because even the urban poor, they tend to live in areas where there's less greenery, less trees, and that affects them a lot. So when we look at the global numbers, what you find is the poorer population tend to live in areas with elevated heat. So as urban planners, we just ended up looking at all these issues and how we address it. We always had to, it gets down to too much a micro level. I think Marcel will speak about how we model the microclimate, and then in terms of temperature at a more localized level. But when we're designing cities, we had an issue of how do we quickly address or identify where there might be problems. So we work with our digital team, our engineers. We came up with this tool which helps us sort of quickly assess where there might be problem issues when we are designing a city. So it allows rapid complex modeling. Just tell us, is there a problem here? Is there a problem there? What do we have to do to address it? So it takes into account a number of factors, which I'll show later. So it's built upon using remote sensing, a lot of data processing. The inputs would be your building mass, your building fabric, anthropogenic heat, as well as surface cover. And then we blend it in with a Suez model, which is the urban energy and water balance scheme, to give us a result at the end. So there are challenges for a quick review on the urban heat. For example, if you're using remote sensing and then aerial photos, we can't identify whether it's artificial grass or real grass. So that's when we have to go back on the ground to double check to make sure that, you know, what is calculating is actual on the ground. So that's where Marcel's and the team's efforts would be key as a next step once we identify an issue at this macro level. So the influencing parameters, how we calculate UHI, and what the output would be is the process shown here. I mentioned about this earlier. So what we did was we looked at a number of cities across the world, from Cairo through to Mumbai to Singapore. And just some examples, what it highlights is that the temperature variance can vary quite a bit. I think we are seeing numbers from 6 degrees to 8 degrees differences between the coolest part and the warmest part. Proximity to heat, to nature and vegetation and water is really important to bring the temperature down. We are noticing that poorer neighborhoods are located in areas with elevated temperature. And I think I spoke about machine learning and the satellite imagery to help identify the areas and then where the gaps in our system, our tool might be. So I'll quickly run through this. For example, in London, when you're seeing the warmest part and the coolest part, the obvious difference is the hottest part always have a lot of impermeable surface area, less vegetation, less water. Similar for Spain as well, 90% impermeable surface area for the hottest part, and the coolest part had over 90% vegetation cover. Similar for Mumbai, where the coolest part has more vegetation, wetlands, water, example. And New York, the coolest area is also where the park was. When we model it for Singapore as a whole, for the other countries, we tend to take 150 square kilometers, but in Singapore, besides doing the 150 square kilometers, we also look at the wider Singapore. The coolest part was Upper Pierce Reservoir. And surprisingly for us, the warmest part we found was next to our office in Telok Ayer. Telok Ayer, if you know Amoy Street and Telok Ayer Street, is low density. It's 2-3-story shop houses, apart from a couple of towers. When we looked at it a bit closer, we realized obviously it used to be near the water, right, before the reclamation happens. The higher buildings have sort of created a canyon effect to not allow air movement as much through that area. We noticed that the roofs of all the shop houses were really dark, and the short distances from your heat built up into the walls, into the ground, into our sort of human level is throwing the heat very, very quickly into the street level as well. A lot of air conditioning units which are throwing heat into the area at Telok Ayer. So in terms of the hottest and coolest, I won't have to repeat this. The coolest area all has lots of water and grass and trees at Upper Pierce Reservoir. And the contributing factors can be anything from, when we're looking at it, from the types of and colors of your roofs, thermal massing, from transportation. If there's lots of car movements there, it contributes towards it. And then green space plays a key role as well. The things in terms of mitigation, I think you know where this is in Boat Quay, the amount of air conditioning units throwing heat into the atmosphere. To adapt, I think we are looking at facades if it helps, but obviously in discussion, Marcel, maintenance is also an issue, so all those has to be considered. We looked at the Cool Roofs retrofit program for London. If we were to paint all the roofs white, or if we were to put solar panels, how much temperature reduction there'll be. We look at urban forms when we're looking at Doha Master Plan. This is a balance we have to play, right? If you're creating lots of shadows and trying to get the temperature down during the day, if there's not enough air movement, at night the temperature can be elevated for the residents as well. You play with all sorts of shading devices in the urban areas. This is in Spain. You want a lot of water through your design of cities, especially, I think, a simple way to make us adapt to a higher temperatures. Maybe bring back things like drinking fountains, etc., which is easily provided for, which seems to have lost when we're designing cities in the current times. In Singapore, just got voted the safest and water in the world, right, out of 180 countries. So there's no reason not to provide drinking fountains. I think the way forward in terms of how we holistically look at addressing urban heat, there's a lot of data needed to help us to come to the right conclusions. So for example, when we're looking at Milton Keynes in terms of planning for heat, this was very focused on the social economic vulnerability. We looked at where the older population were, where the young population were, how do we address and bring down heat in those areas. So we look at where the schools are, high residential population and the makeup, whether they're older or younger. Fitzrovia, here we focus more on scenario building. What if we were to increase tree cover, have more water, and paint all the roofs white? How much temperature it reduced by? Obviously, when we look at the numbers, it worked out from 2.4 to half a degree temperature difference. And then lastly, for Dar es Salaam, we were just scenario building in terms of their planning, current planning and future planning, and how much temperature might elevate by, also building in climate and temperature scenarios in the future. So I think heat is a key area, but for us, generally, what we're seeing in the market is also that from climate change, to make sure that it's more resilient in the future, what risks asset owners are looking at, how we can plan cities better, so it can cover anything from, besides temperature rise and heat waves, to extreme storm, to droughts, etc. So we are seeing a lot of demand in this area to make sure that we plan cities better in the future. Thank you.
Good evening, everyone. So it's our last session before we head for the big break for the dinner. So yeah, so stay with me for a while. So my name is Marcel. So I'm from NUS. I'm representing NUS here and also representing the campus infrastructure. We work together with them as part of this initiative on part of the NUS overall roadmap, sustainability roadmap. So just to give you a background, so NUS has this 10-year program of the sustainability roadmap that have several fronts. They have from the design towards sustainable campus, decarbonize. They also have the waste as well. But in my case, our team actually will work more on the defense against the climate change, and just to bridge what Tony has just mentioned as well about how we want to respond not just on the increasing temperature, heat stress, and also on the uncomfortable outdoor condition as well due to the increase of the heat around us. So yeah, again, this one has been seen by many people. This is taken from the Singapore latest national climate change study for V3. So yeah, temperature is increasing, but I think one thing that people have to take note is not just about the temperatures increasing, but the number of hot days and the number of hot nights. So it's not just about the magnitude that is getting hotter, but how many days that actually this kind of phenomena happens throughout the year. So this sometimes is not mentioned a lot, but the quantity of the number of hot days occurring has been increasing as well. So the quantity and the magnitude both need to be addressed as well, especially in Singapore, that part of the country that representing other urban areas that staying in the tropical climate. So we are working with the campus infrastructure. So part of the campus, we're using NUS as a living test bed, as a living lab. The idea is that we're using this BEAM workflow from baselining, evaluating, action, and monitoring. So the bigger arc is that we want to conduct data collection. So if in order for us to conduct microclimate assessment, data is important. You want to know what is the past, present, and future. We also doing this simulation, but the simulation will need this data-driven approach. Then one of the main goals is that we want to make sure that we want to improve the outdoor thermal comfort. We want to make sure that our campus inhabitants, they also not just staying indoors, but we want to make sure that the mobility across the campus. If you've been to NUS, so you know that I give you an example that NUS is quite big. So the mobility between the staff and the students are quite high. We have to move around between the buildings most of the time as well. So we want to improve that. And also the campus has this one big campaign about planting more trees. So they have a target of planting 100,000 trees for the from 2020 to 2030, so about 10,000 trees every year. So we want to support that campaign as well with our data-driven campaign on you're not just putting certain trees at certain location. We want to make sure that they also can plant those strategic tree planting in order to maximize the potential, not just on the shading, but also on the improving the thermal comfort as well. So yeah, we have a website. It's an ongoing development, coolnus-beam.sg. We have a digital twin platform which we can play around to see what kind of data, microclimate data that we are collecting at the moment, and also some of our, we also play around with the data. We also play around with some geospatial data, and also we also collaborate with other researchers. So we are trying to push as many findings that we can into the platform. Yeah, so the four main components, the baselining. So baselining is about our assessing historical data. We look in the past, we look in the present, and we also use this as a baseline on what we can improve. So when you want to improve, you need something that you can compare with. That's where the baselining is. And from there, we conduct our evaluation. So I think UHI, we try to identify where the hotspots, and we try to zoom in into the hotspots. Then we try to conduct some assessment. Okay, what is the actions, feasible actions that we can provide into those several locations? And we always try in a small scale. We do test bed before we upscale it. If we want to, before we conduct it into the whole area, we try to test it in the room or in the small scale in the building, certain buildings, before we say that the feasibility, the ROI, the performance is there. Then we move on into those bigger scale. And of course, monitoring. We install about 40 weather stations and other sensors across the campus. With this high granularity, we hope that we can detect those areas that require certain mitigation strategies as well. And we try to put everything all in our digital twin. So this is a snapshot of our digital twin where we this one is the snapshot of our 40 weather station on the rooftop and also on the ground level. Ground level is about 2 meters high. Then from there, this is where our climate sensing data are obtained. Then from there we conduct the hotspot identification. Then we do the mitigation test bed, and of course then from there we try to upscale our mitigation test bed throughout the campus scale, in which we also conduct simulation on microclimate, the CFD or the urban ventilation, and also energy data as well for certain buildings or in a group of buildings or district scale. But one key mitigation that we try to focus also on the greenery as well, which I will talk about it more later on. So the snapshot of the data set that we have collected is that for the weather stations, we also installed thermal cameras. We also want to know what is the surface temperatures on the not just on the building facades, but also on the horizontal surfaces as a rooftop. We are also because we are also installing a lot of PV panels on the rooftop. Some of them are combined with the rooftop greenery. So we try to see on the long-term basis what is the performance and how it affects the microclimate as well. And apart from these weather stations, we are collecting the typical weather variables. We also have some meteorological towers. So meteorological towers means that it's a 15-meter story high the microclimate sensing. So we also want to know what is the vertical profile of these weather variables. Then, yeah, so these are the data that we are trying to, we have been collected since January. So we hope that after 1 year full data collection, we try to come up with some findings on what's happening in our own backyard. Coming back to one of the key mitigation are the trees. So I believe everybody knows that, yeah, trees they provide shading. They are doing this cooling thing through evapotranspiration, more heat reflected, less heat absorbed, and they don't produce any heat. Then we compare with our man-made structures in the urban areas, so they are doing the other way around. So we always in our group we see that greenery acts as a natural cooling system, so significantly lowering temperature and enhancing thermal comfort. So looking at this subject, I believe that NUS has been doing pretty good, like maintaining the tree conditions across the years. So we also working on the top-down level. We are looking at using the remote sensing. We have identified that across the years, NUS has maintained this non-built areas and the green area relatively the same. About 40% are built area and the rest are the greenery area. But as you can see that in 2019, you can see the portion of the greenery area, about 35%, 36% are tree canopy area. And with those additional tree planting, we can see that across the years, the greenery area that shaded by the tree canopy has been increased. And I think in the latest one, we can see that most of the open areas, minus the open running fields and everything, we have most of the tree canopy have covered most of our green areas then. So not just we are not just identifying where are the green areas and the non-green areas, but we also building our first campus greenery database in which we not just we identify where are the tree location, the 3D models, the terrains, the turfing areas, 3 dimensions. So one of the thing that you see here is that we have identified the species, the gut size, the canopy size for every location. The idea is that once we did this tree management, we also want to make use of them into our microclimate assessment, our simulations, and also when we conduct our tree pruning and also tree maintenance, we also working with the campus infrastructure for the operations in order for them to atomize and also making what are the tree facing of the new tree, what are the new trees, the scheduling, everything. So we try to make use that, okay, we want to know where are the tree conditions in our own backyard. So for each weather station, for each our location, we also want to see, okay, so if you want, what is the microclimate condition for each location, how it is affected by the surrounding condition as well. So we try to quantify the buildings, the amount of the the hard surfaces, the amount of the shading from the building, amount of the shading of the trees. So we can see that each of the location, as what Tony has mentioned, that from one neighborhood to another, they might have a different profile. So we want to quantify what is the actual factor from your urban morphology that actually affecting those microclimate conditions. Then from there, we are working with some machine learning process on how we want to use like climatic mappings in order to illustrate the overall condition of our campus. Then using a long-term data series of the data collection, we can actually see throughout the months, throughout the different months, different or maybe even different hour or different weeks, we can try to develop these climatic mappings in the series. As I mentioned before in the beginning, we not just want to see the magnitude, but we also want to see like what's happening in different seasons. Singapore is quite affected by the monsoon periods, dry monsoon, inter-monsoon. So it means that you see that the blue ones, December is our wettest period, but sometimes different years have a different impact because of the El Nino, La Nina, or we imported smoke from our neighbor Indonesia as well. So there's many factors actually affecting what we can say that the days where the days are hot and hotter is also affected by not just by our urban condition, but also by the bigger scale of this climate, how the climate works. So because of those, we try to zoom in into several locations. So in this case, we can see that from our climatic map, we try to identify where are our hotspots as well. In this case, we can zoom into, let's say, in one of our residences, the Prince George Park residence. So using the same data set that we have collected in the beginning of all the trees and also the buildings on the baselining process, we can do more specific. Now we're going into more like more isolated like small scale, in which we also include all those tree databases that we have collected before. Then from here we can see that the trees, if we look into the radiant heat, so it's not just temperature but the radiant heat as well. So we can see that mostly the shading plays a big role. The problem with our campus is that once we go down into the lower level, the wind condition, the ventilation apparently is not so good. So it means that you can say that, yes, we try to improve the wind condition, but apparently in our case, we felt that the shading, because it's a more permanent structure, it provides more comfort compared to if we have to try to enhance the wind flow, because based on our data for about a year, our wind flow across the campus, yeah, on and off, is not always stable. And so this one gives us a big challenges as well. And then we also try to see not just on the outdoor condition, but also on the building level. Let's say this one we try to see, okay, based on our shading from the greeneries and from the surrounding buildings, if you want to apply, let's say a cool paint or solar film, do we need to apply to all the buildings or all the facades? Probably not. Some of them have the self shading from the surrounding, so we can just target those that really affected by this exposure from the sun that can go into the first priority. This one, because most of the NUS buildings are like older buildings, so we cannot always like build new ones. We try to do a green retrofit to most of the buildings. Then we try to identify the pockets where are the main pathway or the main circulation for the students and also for the staff, and how we can improve those pockets as well to make sure that people not just stay indoors but also make use of the space outdoors to improve the social life as well. Then sometimes our management also try to say, okay, we want to plant these 10,000 trees. So can you give us like the numbers of the benefit? The issues one we can say, we go into different location with different type of greenery, different type of density of the greenery. Then we try to see, okay, if we put some sensor above, sensor underneath those different locations, we can see like this location number 5 and 8. You can see that just looking by the air temperature, for this only gathered from the 2 months period. You can see that from those open spaces and from those underneath the tree canopy, what kind of the approximate of this temperature differences that you can see between these two distinctive conditions. Then apart from the greenery, we also, as mentioned before, we also look into the cool pane. We did a whole building. This is the good thing about using campus as a living lab. If you want to do this outside, you might have to deal with a lot of different agencies, and not many building owners want their buildings to be tested with this kind of trial and error. So we have a benefit of using our own buildings to be test bedded. So we paint the whole building, this facade, especially with the cool paint, and also we put the solar film on the windows as well. Then we did like 2 months of the data assessment, not just on the heat gain. We measured the indoor condition, but we also tried to test out. We also hire an energy service company to tap on the energy data as well for 2 months. So we want to see that, okay, so it reduced the direct heat radiation from the sun, but how much it actually affecting the cooling load. Then from there we can aggregate, okay, how much saving that you can get if you try to apply this. And we try to see the neighboring buildings. We want to do another test bed. Perhaps we can also use the energy plus simulation, if without shading and with shading, where are the pros and cons. So all these things we try to do it in the building level, and we try to upscale it if we can get a good performance as well. So that's how we can also work with the industry on the supplier as well to make sure that this mitigation options has been tested as well. Then we also conducted one of the hotspots we've seen is that the car park spaces or the roads that one of the major hotspots is that because they are not shaded as well, and they're also our thermal like heat sink as well. So we did some cool pavement tests. Then when we tried to put them side by side, one in the control without cool paint, another one is the cool painted. Then we try to see across the months, what is the efficacy and efficiency and how they perform. In short, not so good. Because cool pavement is only good on the brochure in a way, because they do it in the lab with a very smooth surface, but on the roads it's not smooth at all. And we did it in the car park because we want to test that how long that it will last after the cars are coming in and out. And so the temperature improvement is not that much. Then from there we realized that maybe it's not the coating that can work better. Maybe it's the bitumen itself that you might need to change the composition, because the coating you need to apply after some time you have to repair again. So in a way, bad findings also a good finding for all of us as well. We tested, so you don't have to test it outside again. Then, that's apart from here. There are other things that are currently ongoing on different locations. One of them that we tested the difference between the artificial grass and the real grass. In thermal perspective, the real grass, yes, they really perform much better. We found out that the artificial grass perform as the same as the basketball court, but of course in the term of maintenance and if we talk about the cost, yes, now you talk about a different aspect already then. So apart from that, we also want to know what is our ventilation condition. So urban ventilation, we are working with the Kajima as well, because they are able to conduct like this big scale CFD simulation. One key thing that make us this different from the others that we try to include that many trees inside our CFD simulation, because usually when we did our CFD simulation, we tried only to see the terrain, the buildings, the trees, because it's very highly computational demanding. They try to, and sometimes people don't have the data as well on the vegetation, but we try to make use most of our vegetation data in order to know that the ventilation will be highly affected, especially on the human level, because the tree actually they slow down the ventilation, but they provide the shade so evapotranspiration against versus the wind flow. We try to make use that, okay, can we generate our wind corridor based on our weather station data? We realized that our sea breeze from the south is very strong, but only on certain months as well. So we hope that from the 1 year data, from the data collection, we try to see the profile of this prevailing winds across the months. The idea from this cool NUS beam is we need to collaborate, like me and Tony and other people. We have different targets. Some people want to make sure that the indoor comfort is good. Some people want to make sure that outdoor comfort is good. Some people target certain different profile as well, energy. So yeah, so we need like different people to work together using the same data set as well. So we try to, and because we want to maximize our campus as a living lab, so we already like talking to different departments. We not try to be siloed and try to emphasize on our ego as well. We always trust on the data first. I know that people like try to work on a lot of simulation, but in our case, we try to see, go from the data first. We try to capture what is the present and try to see what is the behavior, what is the profile across the time. And ultimately, we hope that we can try to replicate our framework beyond our campus. We hope to inspire like people outside our community in order to adopt these sustainable or climate resilient practices. And hopefully, we can do the changes together then. Thank you.